Hello everyone, welcome back. So in this video we are going to be discussing about why concrete needs steel bars or steel reinforcements. So just before we start this lecture, just to let you know that this is one of our lectures of reinforced concrete designs subject, and we have our YouTube channel in which we are uploading the lectures related to reinforced concrete design in detail. So you can check out all the other lectures and maybe they will be useful for your studies. So let's continue this one. So in this lecture, we're going to be discussing about why concrete needs steel bars. Now, in the previous video, just before this one, we introduced the word or this word that is reinforced concrete designs, and we discussed that what is reinforcement and why do we study this in engineering, right? So we just discussed some basic uh, terminology and its information in the previous lecture. Now in this video we are going to be discussing in a little bit detail that why concrete needs steel bars and what is the problem with the concrete that it can't handle and the steel needs to be provided there. Why can't it be done without the steel bars? So let's discuss that. So you might have seen normally in the construction sites or anywhere whenever you're passing by somewhere where there's a construction happening or in your own house somewhere, maybe there are steel rods that are visible there, and even constructed houses sometimes there are those steel bars visible, or maybe under construction sites have the steel bars all the time present somewhere there. The laborers are working with them, right? So there are a lot of steel bars that we're using in our construction buildings and structures, but why do we require that? Now, to answer these questions and to understand this, let's first of all discuss about concrete. Then we will discuss about the steel bars. First of all, let's discuss that what is concrete, why do we require it, and then where is the point where we need to introduce something other than concrete because concrete can't handle some things, right? So let's see. Let's first of all discuss about concrete because the concrete and the steel both combinedly are added in different parts of the structure. So let's first of all discuss about concrete. So let's see here. Normally you might see different combinations of concrete and steel bars and they make different structural components. So they can be beams are horizontal members of structures and they handle different sort of loads. Then we have columns which are vertical, we have slabs, and we have walls and different other parts of the structural components, right? So the beam is also one of the parts. Now in the beam, if you're using concrete, so let's discuss some properties of concrete, some basics of the concrete. So concrete, you might have seen, is usually a mixture of different materials, right? And those materials usually are like um, cement, and you can see fine aggregates, you can see water, coarse aggregates, admixtures, and air, right? So cement, you might normally see that it is one of the very important element or material that we add in the concrete to give more strength to the concrete to or to glue all the different parts that we're materials that we're adding to the this mixture, right? So cement acts as a sort of a glue uh, that actually makes all the different materials uh, stick to each other and not uh, to be separated, right? So it's that sort of a element. Then we have fine aggregates, we have coarse aggregate. Fine aggregates are smaller particles or smaller materials, and coarse aggregates are more larger in the size, right? And it depends on the different uh, it depends on different situations and different it depends on the purpose for which we are constructing a different set of a component, and on that purpose we actually decide that how much material of fine aggregate or smaller particles are we going to be adding and how much are we going to be adding the larger particles that are the coarse aggregates, right? So it depends on the situation, on the type of the material, on different things, and based on that we do some calculations and we decided how much amount of these things we have to add. Similarly, water, we add water and we also have to calculate and we have to decide at how much water do we require, right? Because adding them more or less or any quantity will actually affect its quality and its different other functions, right? So based on those things and based on our requirements, we actually decide how much we have to add there. So there are these combinations actually make the concrete, right? Now you can see in this picture that how these different materials are mixed and they are being poured down on a sort of a somewhere maybe on the reinforcement bars, and something is being constructed, right? So let's discuss about the properties of this concrete. The concrete is actually good in something and weak in something. It's the property of everything in the world, right? Everything is good in something and maybe weak at something. So what is concrete good at? Concrete is good at compression, but it is weak in tension. Now, compression, you can see in this image even that compression is when you apply a force and just try to somehow reduce the, or somehow try to stress them and reduce the cross-sectional area or lengths of them and just try to just apply a force on them, right? So you can see that these are some cans which are normally larger in size and having some heights, but when you compress them, so they just lose their uh, areas and they lose their lengths and everything, and they're just shortened, right? So this is compression. And then there's tension, in which you actually try to elongate the things. You try to pull them apart and you try to elongate them. So everything is not having both of these properties, right? Some of the things are good at handling the compression, and some of the things are good in handling the tension, the elongation. So the concrete is a member which is good in handling the compression. Now let's say if you see, for example, this block of concrete, which is made of concrete, right? So if I just try to increase the size of this block, so you can just try to imagine that this concrete is made up of different sort of aggregates that we discussed: fine aggregate, coarse aggregate, smaller particles, bigger particles. So if you try to apply a force on them from both sides, like if I just try to draw it here with a black color maybe, from this side and from that side, so what's going to happen, that force is going to be transferred to maybe a aggregate or a stone somewhere, and then to a smaller one maybe, and then to another one. So all different particles are going to be, the force is going to be acting on all those different particles like this, and it's going to be transferred to another one, then to another one. There are a lot of particles that I don't think we can count, but you can imagine that how this force is going to be transferred from one to another and to another, from that side as well. We can see some forces are going to be acting from that side, some from this side, and that's how it is going to be able to take that compression. If you apply the force from both sides, those particles will transfer it from one to another, from one to another, and it will handle it somehow. It will be able to sustain that load and everything. So that's why it's good at taking the compression. But if we now imagine the other way around, in which you're applying tension, let's say you're trying to pull them apart from each other. So that's where the particles can easily separate from each other, because they're just maybe this time not being able to uh, handle that uh, joint joint that they have actually made with each other through cement or through something. So they will not be able to uh, somehow hold their hands and be able to stick to each other, and they will be separated. So maybe if you just apply this force, tension, which we call tension, they will separate somewhere here, and they will just lose their bond and they will just move apart. So that's why we say that concrete is bad at tension. So this is just a weird example that I have given to you, but you can just understand it this way better, right? So this is the property of the concrete. If we get back to it, that concrete is good in compression and bad in or weak in tension, right? So this is the one property. Now let's go to the steel. Let's discuss about steel. Now steel is opposite to this. If we discuss about steel, so steel is weak in compression but good in tension. And you remember the concrete was good in um, compression. Okay, and I think there's one thing that I need to correct. The correction needs to be done for weak. Weak is actually. Okay, sorry. So yeah, the steel is weak in compression, is good in tension. So you can see that if we needs if we need material or if we our requirement is that the structure should be able to handle compression as well as tension, so only concrete won't help because it will be able to handle the compression but not the tension, and only steel will not be able to help us because it will be able to take tension but not compression. So we need the combination of both of these materials to build a perfect member that will be able to handle both compression as well as tension. But that's not all. There are a lot of other things that we need to understand as well. And this is just the sort of a basics in this specific subject of reinforced concrete design. There's a lot of detail on this subject, and the engineers and the people to spend their lives doing researches and doing studies related to these subjects and trying to find more information that is best for the site and for the constructions, right? So this is just basics. Okay, now let's discuss a little bit more. Let's go into more detail. Maybe let's just try to take an example of a structure, right? But before the structure, you can see that how the steel bar is bended here, and you can see it's not cracking or something. So what usually happens in steel bar when you apply a sort of a tensile force and when you try to pull it apart from each other, when you apply tension on both sides. So what happens in the steel rod is, which is not happening in the concrete, is that when you pull it apart like this, so what's going to happen, there is an elasticity till a certain limit in a steel, and that's why it is going to be, where is my marker? I cannot see it. Okay, it's here. So it is going to be just elongated like this, like this. It's going to be elongated from here. It will, from middle it will become thinner, and from the sides it will be kind of okay, right? And that's how the tension will be acting on it. And then there will be necking means it will become very much thin. Like there will be a certain point that it will become very much thin when you keep on applying the force, like it will become something like this. And after necking there will be a crack or fracture, and that steel rod will fail. So this is what the steel rod basically can do. It can handle the tension till a certain point. It can bend, it can elongate, it is elastic. And if you keep on applying the force, it will be elongating until there is a something beyond its limit and it fails, right? And this property of elongation in the steel is what actually is very helpful for our structures and for our designs, is very helpful, and you'll find it out in our upcoming lectures at how. Like if I give you quickly one example, is that this elongation actually gives rise to cracks, and those cracks are actually normally we would think that these cracks are not good, right? Because they don't look good on our structures, and they actually uh, make us think like if the structure is going to fail. And yes, the structure is going to fail if there are cracks and they're not good. We need to repair them. But the thing is that imagine if there were no cracks and the structures would fail suddenly without even giving you any cracks, then what would happen? That would be more dangerous. So it's good that we can see the cracks, and before the structures fail, we can actually repair those structures or those different components of our structures. And you know why those cracks appear? Those cracks appear due to different reasons, but one of the reasons in our reinforced concrete components is the reinforcement. The reinforcements are the things that are actually holding the structures and giving you time to repair the structures, and it shows you those cracks. And those cracks are due to certain reasons of the reinforcements being there. So because there is reinforcement, the concrete cracks, the reinforcement is still there, it is giving you time, it is giving you a warning that this structure might fail at any time, so please repair it, right? So reinforcements are actually good, and cracks are also good, that they are actually sort of a warning for you. Okay. So let's move further. Now let's discuss it through the help of this structure that we're having here. Now, in this structure, we are having different combinations of beams and columns and different other members. So let's take one member from here. Let's say this is a sort of a beam, let's say. And in this beam, if you see, there are different forces being applied from the top. There are different members, and there's this column, and there are maybe other steel members and everything, and maybe there are chairs and tables and other things in the future on top of that beam or slab, and there are people there. There are different sort of loads, right? So those loads are going to be applied on this member, and whenever they're applied on this member, which we can see in front of us, is going to be experiencing those loads, and those loads are going to give rise to a certain sort of a bending phenomena. Right, now how is this going to be, how is this bending going to be? If I show you this image here, let's say this is how that bending is going to look like. This is the member that you can see, and under immense load, that beam that you can see here at the top is going to be failed like this. It will be having compression at the top and tension at the bottom, and it will have cracks at the bottom, and it will fail. Now let's see it here. Let's get back to the previous image and let's discuss it here. Like if I rub this from here, so what's going to happen, let's say this is the load from the top. I'm just showing one arrow, and this is the beam. So what's going to happen, this member will actually try to bend something like this. This will bend like this, and this will bend like this. So it will bend something like this, or it will, and under immense load this is going to happen, right? Normally our structures don't bend or don't fail. Why they don't fail? Because they're perfectly built and planned, and there are reinforcements in their concretes. But let's say you apply more than the load required. There can be a limit to every sort of load that you're applying to structure. Let's say you apply too much load, then what's going to happen, this structure is going to bend like this, and eventually it's going to, if you keep on applying more load and more load, so there will be failure from the bottom or from other parts. It depends on the situation, and it will crack and it will fail. So what's the important thing to understand here? Important thing is that there is actually compression and tension here. And where's the compression and tension? I told you in the previous slide as well that the compression is going to be here. You can see that this member is actually trying to compress. It's whenever something fails like this, so the upper part is actually just coming near to each other, it's compressing, and the lower part is actually going away. So that's tension. So I can write it here T, and I can write here compression. And if I show it again to you in this image, you can see this is what I was trying to read. The upper part actually compresses, the lower part is actually in tension, it just goes away. So because there is tension and compression in this member, we need to provide such members or materials or elements that can handle this compression and tension, right? So if I provide only concrete, that's not going to help, because the upper part will be fine, but the lower part will fail. If I provide only steel and at the bottom, then what would happen? The lower part will be fine because tension will be handled, but the upper part, the steel cannot handle the compression. So we need to provide both, not just one thing. So that's why we require steel in the concrete, and we provide them just to make sure that the structures can handle both type of these stresses and loads. Now, another example here. What would happen if there was a beam without reinforcement? How would that look like, or how would that fail? Let's say quickly, let's just quickly try to construct a beam here. Let's say this is a beam, and if let's say there is no reinforcement, so if the load is applied, so what's going to happen, that this upper part will be under compression and the lower part will be under tension, and it will look something like this. So now the upper part will be under compression and the lower part under tension. So the concrete would be like, okay, I can handle the compression, right? I can handle the compression because compression is no problem for me. So the upper part will be fine. But the lower part, concrete would be in a problem there. Concrete would say that I cannot handle the tension and it will fail from the bottom and it will suddenly just crack and just just fail and buckle and just gone, right? Even you won't get any warning or time to repair that, right? So that is totally uh, worst design that you can do for a beam. If you provide reinforcements, then what's going to happen? Let's do that one as well. So here's, let's say, another beam. In this part, you have to design this uh, beam with reinforcements at the bottom. So that's why if you see in the members, mostly in the structural components, the reinforcements are at the bottom, the concretes are at the top of them. And you know the reason, because the tension is at the bottom, right? So that's why they would provide the reinforcements, let's say here, and it depends on how many bars they're providing, but at the bottom. And now if you apply a load here, so the things will be fine. But let's say if you try to increase the load, if it increases its limits again, there will be sort of a compression at the top and tension at the bottom. So now what's going to happen if it increases its, if you keep on increasing the load more and more and more, and it increases its limits as well. So now what's going to happen in the worst case scenario, that at the bottom you'll be having tension, at the top you'll be having compression. So if the compression increases, if the compression increases, it means that the concrete is going to be having problem in handling that. Maybe there's a limit for the concrete to handle certain sort of compression. So let's say the concrete can no longer handle the compression and it have reached its limits. So what's going to happen there? The concrete will just, there will be some cracks that will appear at the top. If the tension increases and it goes beyond the limits of the steel, there will be cracks at the bottom that will be like this. It will not fail suddenly. There will be cracks. The cracks will mean that concrete or steel is still handling the things, but it is in problem. So you need to take care of it. So those cracks will appear, right? Keep on increasing it, the cracks will increase. Keep on increasing the load, the cracks will increase from top, from the bottom, and eventually if you don't repair it, if you don't take care, eventually the things will fail and it will just be gone, right? So what happened in this case was that it can handle the tension, it can handle the compression, and even if you go to the worst loads and if you apply so much load, still it will be able to handle it. It will give you cracks and it will give you enough time to repair it, and you can just repair it and just get back to the perfect structure. So normally the structures that you're having in your house or in your buildings where you're living are actually reinforced concrete designs or reinforced concrete structures, and they are actually stable because at the top you're having enough concrete to take the compression, and at the bottom you're having enough reinforcements or steels to handle the um, tension, right? So the tension is here, the compression is here, concrete is there to handle compression, steel is here to handle the reinforcements, and you have constructed it in such a way that it can take your loads, your structures, your different chairs, tables, and computers, and bed, and different other furniture loads can be handled by your structures because you have provided enough concrete and steel according to the requirement, and that's why everything is stable. So that's why you need reinforcements of concretes. I hope you understood that. In the next lecture we'll come up with another um, good topic. Till that, thank you very much. Take care, and make sure you leave a comment, like, and subscribe if you understood the lecture. Thank you. Take care.